Now let's go over to problem 20. And problem 20 states, carry out the following steps to show that 1 divided by 1 times 2 plus 1 divided by 3 times 4 plus 1 divided by 5 times 6 plus 1 divided by 7 times 8 plus etc. Equals to ln 2. So now it's given us steps to follow to show that. So that's pretty good. So part A, use the formula for the sum of a finite geometric series to get an expression for, so this right here. So 1 minus x plus x squared minus x cubed plus plus 2x plus x to the 2n minus 2 minus x to the 2n minus 1. And then part B says integrate the result of part A from 0 to 1 to get an expression as an integral for 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus plus 1 over 2 n minus 1 minus 1 over 2n. And then we're asked in part C to deduce from part B that the absolute value of 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 plus plus 1 over 2n minus 1 times 2n minus the integral from 0 to 1 of dx over 1 plus x is less than the integral from 0 to 1 of x 2n dx. So a whole lot of mumbo jumbo. And then part D says use part C to show that the sum of the given series is ln 2. Alright, so let's jump right ahead to solution to part A. So let's just jump to the solution. So part A says use the formula for the sum of a finite geometric series to get an expression for this. So we have this 1 minus x plus x squared minus x cubed plus plus x to the 2n minus 2 minus x to the 2n minus 1. So, and then it says use the finite geometric series. So recall the sum of a finite geometric series. If we have the sum at the nth partial sum equals 2 Sn equals a plus ar squared plus ar n minus 1, and then Sn is equal to a times 1 minus r power of n, all divided by 1 minus r. So in our case, we have, well, let's just write the general one here. Sn equals to a plus ar, so plus ar squared plus plus ar n minus 1. Yeah, and then this equals to, I'll just put this whole thing here. So a1 minus rn over 1 minus r. Alright, so that is just a general, the general nth partial sum for a finite geometric series, and there's the equation for the sum of it. And now let's write this out and see how we could use that formula. So we have 1 minus x plus x squared minus x cubed, and also notice the way they write it, 2n minus 2 and then 2n minus 1. So we get here, so in our case we have 1 minus x plus x squared minus x cubed plus and yeah, I think that's what we wrote. So yeah, minus x plus x squared minus x cubed plus and then plus 2x plus x 2n minus 2 minus x to the 2n minus 1. Alright, now we need to see what matches up. Well, we have here a is 1. So we just write our a equals to 1. Like that, I'll just put the arrow above here. So a equals 1. Now the r, well, the r is right here. So if a is 1, then this r is right over here. And yeah, we forgot to add the AR. So let's move this all the way to the right side. Plus AR plus, yeah. So that lines up. So AR plus AR squared, etc. And then we have this R. So A is 1. R is going to be here. R equals to just negative x. Yeah, so that's just r is negative x. And then what we'll have is, well, negative x times negative x is going to be here r squared. That just becomes positive x squared. So that's this one here. And we could see that. And then notice here, this n minus 1 this matches up with, if this is the n minus 1 supposed to be this, and then notice how there's a n right there. Yeah, and basically what's happening here is this n is, in this case we have n is equivalent to 2n. Or another, basically this n, this one right here, this n, I'll just put that again. So the n is equivalent to 2n, and the reason I'm putting this 3 lines because the variable's already there, n and n, and we're not saying the same thing, we're just saying that it's equivalent to. So this n is replaced, is equivalent to this 2n in this formula. Because right here I could write a equals 1 because there's no other a variable. And I could do r is equal to negative x, there's no other variable, but this one is already n there. So this means that we'll get the sum is going to be 1 is our a, times by 1 minus negative x 2n. So we're not going to put n there, so the n becomes 2n. So there's a 2n there. And I'll remove this line like this. So put this 2n, and then I'll divide this by 1 minus negative x. So this means is this whole summation is equal to, do a bunch of simplifications, 2n there is, well, this is always going to be positive because it's always an even power, and so we're just going to be left with this minus by itself. So it's going to be 1 minus x to the 2n over 1 plus x. So that's what the sum of this finite geometric series is. Alright, so now let's take a look at the solution to part B. So part B says integrate the result of part A, so this one here, from 0 to 1 to get an expression as an integral for this setup here. Alright, so which is a 1 minus 1/2 plus 1 cubed, plus 1/3 plus 1 over 4 plus ... 1 over 2n minus 1, and then minus 2n, and minus 1 over 2n. So integrating is a solution to B. Integrating the result from part A from 0 to 1, we get, so put this in the integral. So we're going to go integral from 0 to 1 of 1 minus x plus x squared minus x cubed plus ... and then minus, this is going to be, actually no, it goes all the way to plus. Let's see how it goes. Yeah, this the way it's written, it goes minus here, then eventually it's going to be a plus there, minus there. So plus all the way to x 2n minus 2 minus x 2n minus 1. Like that, dx. And now this just equals to, well, integral from 0 to 1 of our sum of the finite geometric series, 1 over x 2n over 1 plus x, and then dx. Alright, so what I'll do now is, well, I'm going to integrate all this and evaluate it, as well as this as well. I'll just separate that into 2 integrals. So what we're going to get is, this is equal to, the integral of 1, or the antiderivative of 1 is just x. So we're going to go up, this is going to be x. This next one's going to be x over 2, like that, 2 over 2, like that. Again, using power, just the antiderivative, power functions and antiderivatives or integrals. And again, this is x squared. This is going to go 3, to increase the power divided by 3. Next one's going to be x4 over 4 plus ... The next one is going to be here, so we're going to subtract we're going to add a power, so x 2n minus 1, and then divide by that, 2n minus 1. The next one here, add a power, minus x, this is going to be 2n over 2n, like that. And we're going to be evaluating this from 0 to 1. Now this whole thing equals 2, and I'm going to put it on the right side now. So that was the left side, this is the right side. We can just divide this 1 plus x into 1 and into negative x 2n. So we get a 0, 1, then 1 over x, 1 over 1 plus x. So we get two integrals, 1 over 1 plus x dx plus, or actually minus, because of minus sign, an integral from 0 to 1 of x to n over 1 plus x, and then dx. So that's what we have. And now we're going to evaluate this. We're going to put the 1 in each one and then subtract from 0 in each one. When we put in 0, well, we just have 0 to the power of whatever. Those all vanish. So all that matters is this right here. It's just the 1 is all that matters. So we get equals 2, 1. So when you put in 1, it just becomes 1. 1 over 1 over, 1 minus 1/2 plus, then we get the x cubed, just 1, plus 1 over 3 minus 1 over 4 plus dot dot dot, then plus, then this becomes 1 over 2n minus 1, and then minus, this becomes 1 over 2n. And that equals to the integral on the other side, 1 over 1 plus x dx minus integral 1x 2n 1 plus x dx. Yeah, so we have all this. I'm just going to box this out like that. And there's a 0 here that got messed up somehow. Like that. Alright, so that is the 0. I'll move this a bit lower. And this a bit higher. Alright, so now we have expression. Yeah, or the expression for the one that we were given, and this equals this integral. So then we can solve question C. So let's go back to this. So again, we were told integrate the result of part A from 0 to 1 to get an expression as an integral for this. So yeah, so we wrote this 1 divided by, 1 minus 1 over n plus 1 over 3 minus 1 over 4, etc. All this as an integral. And now we're asked in part C to deduce from part B that the absolute value of 1 divided by 1 times 2 plus 1 divided by 3 times 4 plus 1 divided by 5 times 6, etc. And then all the way to 1 divided by 2n minus 1 times 2n. And then subtract this by integral from 0 to 1 of dx over 1 plus x. And then absolute value of all this is less than the integral from 0 to 1 of x to the power of 2n dx. Alright, so let's take a look at the solution to part C. So part C, the part C, we got to get it in this giant absolute value sign. And notice this 1 divided by 1 times 2 plus 1 divided by 3 times 4. And notice the square root from 0 to 1 of dx 1 plus x. And that we have this set up here. So we have this. So the idea is if we can write this in that form I was asking, so solution to C, notice the following. So if we take this segment here, so let's just take that segment. So notice that if we have 1 minus 1 over 2, well, it's the same thing as writing, I'll just write it in extra detail. So if we have 1 minus 1 over 2, this equals to, well, 1 over 1 minus 1 over 2, just for completeness, just to show you the pattern. And this again equals to, multiply the top and bottom by 2 over 2. So 2 over 2. Then we're going to get a 2 minus 1 over this, 2 times 1 is the denominator, or just 1 times 2, like that. And this just equals to 1 over, yes, and this just equals to 1 over 1 times 2. And the reason I'm writing that is because that is in this form here, so 1 times 2 there. And then as you can guess, I'm going to do that the same for the 1 over 3 times 4 and 1 over 5 times 6, and so on. So that's that. And also now if we look at this segment, so right here, let's look at that now. And 1 minus 3, 1 over 3 minus 1 over 4, this right here, is equal to, and again, multiply the common denominator on this side. I'm going to multiply this one by 4 over 4 and this one by 3 over 3. So in other words, we're going to get a setup that looks like this. This is 4 minus 3, and then the common denominator is 3 times 4. So multiply top and bottom on both sides, and then when you multiply it on this one, 3 times 4, the 3 cancels, and this one, the 4 cancels. And notice here, this equals to 1 over 3 times 4. So in all the scenarios, we are going to get, notice this is 1 times 2, or this is 1 over 3 times 4. Let's do, well, there's no more there, but you can see it's pretty much the exact same thing. Then if you continue all the way over to this side and see what happens there, so dot, 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 so then we get 1 over 2n minus 1 minus 1 over 2n, like this. This equals 2, well, again, multiply the top and bottom by each other, so we get the same common denominator. So in other words, we get a setup here, 2n minus 1 times 2n. This equals 2, or we multiply the top and bottom, so this one will cancel. We're left with 2n minus, and then this is going to be minus 2n plus 1. So in other words, minus 2n minus 1, so the minus becomes positive. And this equals 2, well, this cancels, and yeah, we don't need to go any further because that's what we were asked to show. That just remains it like that. So then those cancel, and we're just left with 1 over 2n minus 1, 2n, like that. Alright, so now that we have this, so thus we see from part B, so we could write this all in that form that we were told in the question C. So we get this all here, and also notice here, I'm going to move this over to the other side. So I'm gonna take this and move it to the other side. So we get a negative, negative integral from 0 to 1 of 1 over x dx. So it basically have this side there. So basically we're going to write this out, but before we get to the absolute value side, so that's what we get is a 1 over 1 times 2 plus 1 over 3 times 4, and then plus dot 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 plus the nth one here. This is 2n minus 1 times, I'll just make this whole thing. So 2n minus 1, write this neater. 2n minus 1 times by 2n, 1, like that. And this equal, and then subtracted by. So we're moving over, moving this over to the other side. Subtracted by 0, 1 over x dx. And now this equals 2, and now we're just left with this negative integral from 0 to 1 of xn divided by 1 plus x. Negative 0 to 1 x 2n 1 plus x dx, like that. Alright, so now we have this. We have a bunch of negative, well, we have two negatives there, or this negative there. So what now we'll do is take the absolute value and then show that it's less than this setup there. And we can see that. So what we'll do is, thus, the absolute value, let's write this, thus, neater. Thus, the absolute value of 1 over 1 times 2 plus 1 over 3 times 4 plus dot 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 plus 1 over 2n minus 1 times 2n minus integral from 0 to 1 of 1 over 1 plus x dx. Absolute value, so absolute value here is going to be, well, this negative is just going to be positive, and this is going to be this just becomes, well, the positive of it. So we could, and this one, x to the 2n is always going to be positive, and also the 1 plus x is always positive because x is greater than or equal to 0 there. So this means that this is just going to be positive side. 1 over x 2n 1 plus x dx, like that. And now this whole thing, well, is going to be less than integral from 0 to 1 of x, also there's a 2n there. So forgot the 2n there. Yeah, so x 2n dx. And that's because, well, this 1 plus x, for this integral of 0 to 1, it's always going to be greater than or equal to it. So you can write, so it's less than that since, it's right here, since x to the 2n over 1 plus x is less than x to the 2n for, and I'll put this here, for x is for x is greater than 0 and less than 1. So, but you're integrating from the whole area, when it's when x is equal to 0, then they're just both equal each other, 1 and then equals 1. But then every other value, it's all less than it, and when you're summing it up, it's going to be less than it. All right, so that is what we have. So I'll just box this whole thing because we showed that it is less than that. So that expression that we were asked to show in the question, and we just did. I'm going to move this absolute value higher. I'm going to box this out. And let's go take a look at that question C again. So integral from 0 to 1 of x2n dx. And this is a whole setup like that. And that is exactly what we were asked to show right here. There's integral from 0 to 1 x2n dx. And then part D says use part C to show that the sum of the given series is ln of 2. Alright, so let's jump into the solution to part D, and basically says use part C to deduce that, use part C to deduce, see that again, use part C to deduce, to show that the sum of the given series, which is this right here, and that's going to be inside here, is equal to ln 2. So let's take a look at this. So note that, well, we know these integrals, we can solve these. So the integral from 0 to 1 of 1 over 1 plus x dx, well, the integral of this 1 over 1 plus x, that is, well, we know the integral of 1 over x is just ln x, and this is the same thing, just this, we're dealing with 1 plus x. And you could use substitution and so on, but this is going to be ln of 1 plus x, like that. Because you can see this antiderivative, the derivative of ln 1 plus x is just going to be 1 over 1 plus x. And this is from 0 to 1. So yes, evaluate from 0 to 1. This equals to ln of 1 plus 1 minus ln of 1 plus 0 is just 1. And we know that ln 1 is 0. So this part here, this one goes to 0. So this becomes ln 2. So this is, ln 2. That's what we have there. Alright, so that's ln 2, and now let's solve this integral right here. Yeah, so we don't need to do any advanced integration for this one. We'll just do it for this one here. So this is integral from 0 to 1 of x2n. So we have this, put an arrow, and we have this integral from 0 to 1 of x2n dx. This equals to the this becomes the antiderivative of x2n is x2n plus 1. So I'll put it like this, x2n. So we add a power divided by 2n plus 1, and then evaluate from 0 to 1. So this equals 2, put the 1 inside, we're going to get a 1 to the power of 2n plus 1, that's still going to be 1, divided by 2n plus 1, and then subtracted by, when we put in 0, and then divide whatever, it's just going to be 0. So in other words, this equals to 1 over 2n plus 1, and we can box this out. Alright, so thus part C becomes, and we look at part C, we got this entire giant term, and then we'll have this then it's going to be subtracted by ln 2, and then it's going to be less than 1 over 2n plus 1. So let's write this all out. So this becomes 1 over 1 times 2 plus 1 over 3 times 4. And then plus dot dot dot, and then let's see, it keeps going all the way until 1 over 2n minus 1. 2n minus 1 times 2n, like this. Just fix that up, and now it's going to be subtracted from this integral right here is just ln 2. And then this absolute value is less than 1 over 2n plus 1. Yeah, and going further, so in other words, the nth partial sum Sn of the given series satisfies, and yes, if we call this inside term, this summation that we want, if we call this Sn, so that's the nth partial sum. So what we get is the absolute value of the nth partial sum minus ln 2 is less than the 1 over 2n plus 1. So in other words, we can just take the limit here. So what we'll do is limit as n approaches infinity of the absolute value of Sn minus ln 2. This right here is less than the limit as n approaches infinity of 1 over 2n plus 1. And we know this one right here, you're just going to go over, well, 1 over 2 times infinity, that's just infinity, goes to 0. So in other words, this equals to 0, like that. Yeah, so this absolute value is going to 0, and then we can get rid of that absolute value sign. This basically means that this Sn is approaching ln 2. That's the only way that this can be 0. And yeah, ln 2 is a positive number. So what we'll get is thus the limit as n approaches infinity of Sn, nth partial sum is equal to, and move this over to the other side, ln 2, and we can box this in. And then solution manual just puts a whole term there. So that is, we'll have 1 over 1 times 2 plus 1 over 1 divided by 3 times 4 plus 1 over 5 times 6, etc. plus 1 over 7 times 8 plus ... is equal to ln 2, which is quite amazing. And let's box this whole thing.